can hear me. That's better. Yeah, I work in the Erlang OTP team at Ericsson. And this isn't working either. There. I first encountered Erlang during my master studies, where I focused on distributed Erlang. Distributed systems. And what I love so much about Erlang is its concurrency and distribution model. So I'm really happy to see how the Elixir community is growing now, since it's using the same concurrency and distribution model that I love so much. I have been working in the OTP team for a bit more than a year now. And for the last few months, I've been focusing on distributed Erlang. And that's what I'll talk about here. So you get distributed Erlang. I'll start with how it works today, and then some plans for the future, and then more specifically what I'm working on right now. So you get distributed Erlang or distributed Elixir for that matter, when you have 2 or more nodes that are communicating with each other over the Erlang distribution carrier. We keep a peer-to-peer topology, which means that we don't have any centralized server or something like that to keep the network topology, but we keep all the nodes have kind of the same roles. And by default, we set up a fully connected network, which means that if you connect node A to node B, and then node B to node C, node A and C will also be connected automatically. So everyone will be connected to everyone. What I mean with a node here, in case some of you don't know that already, is an Erlang virtual machine or a beam, which has been started with the name or sname property to give it a unique name, which is used to identify the node. And it's really an operating system process, as you probably know. So you can have multiple nodes on each host, or you can spread them around on different hosts if you want to. It doesn't really matter. On each node, there are many concurrent processes running, and the virtual machine is handling the scheduling, load balancing, and message passing, and so on between the processes. If you use the process ID when you send a message, it doesn't really matter if the process you're sending to is running on the same node as the sender, or if it's running on some other node. Because the virtual machine will handle that for you, and it can do so because there are some node information embedded in the process ID. So the virtual machine will make sure that the message is sent to the node where the process is running, and that the virtual machine on that over there will handle make sure to put the message in the process ID's message queue, or process's message queue. If you use a registered name, which Sasha was talking about earlier, it's not transparent in the same way, because that's only for local registration, but you know all about that right now, I guess, so I'm not going into any details. But you can send the message by specifying the node where the process is running or registered on as well. And this is the API or interface for local registration. But we also provide a global version, which was also mentioned during Sasha's presentation. And it looks like this. So it's through the global module, and you can see the similarities in the API here, or interface. The only difference is that we have a re-register name function as well. The global module is what is setting up the fully connected network. And it's using the full mesh to handle the registrations. So when you register a name, global will first acquire a lock by sending a message to all the nodes in the system. And when it has the lock, it's just locking the name, it's not locking everything, but it's still a lock there. When you have the lock, it will send a message to all the nodes in the system again to ask them to save the name process ID pair locally. And finally, when that is done, it will release the lock. And the same thing goes for the re-registration and unregistration, more or less. The lookup functionality through where is and send is really fast though, because there you have all the information saved locally on each of the nodes. So you don't have to go out on the network to get anything. And one more detail, since Global is handling the fully connected network, when a node joins, there are quite some things happening. One thing, or the first thing is that each of the nodes locks their own partitions, which are the nodes they know about. And then they exchange information about which name process IDs are registered in each partition. And finally, they make sure that all the nodes ping all the other nodes so that we keep the fully connected network. So, how do you think this will work when for hundreds or thousands of nodes? Not very good, right? So everyone is talking about scalability when it comes to Erlang and Elixir, and here I come and say it doesn't scale. What? But this is kind of the next level of scalability, where we're talking about many, many nodes. So this works okay for up to 32 to 50 nodes. But then it's starting to get really slow, and you might have some other issues as well. And we're working in this area to make it scale better. So we have some different issues that we need to look into to solve this. The first one is that if you set up a connection between two nodes, the connection will stay up even though if you don't send any more messages over the connection or any signals otherwise either. So we want to automatically disconnect nodes where no communication is happening. Kind of garbage collecting in inactive connections. But to do so, we need to also remove the need for a fully connected network. And another side effect from that is that we get way too many connections in the network as the system grows. So we really want to remove the fully connected network to avoid that too. The next thing is the expensive node joins that we get. And finally, Global chats a lot. It sends around a lot of messages. So we want to make it less chatty. And all of these we can kind of solve by removing the need for a fully connected network if we do it in a good way. So you can actually avoid this full mesh right now as well by setting the connect all flag to false when you start the nodes in the system. So that might be useful if you want to make your system scale, but then you'll need to handle the network topology all by yourself, so it might add some extra complexity to your code. And you will also not be able to use the global functionality. Okay, let's look at the global again. So we had the registration, re-registration, and unregistrations, which are really expensive right now when the system grows. But the lookup functionality is really fast. So what we want to do is making it possible for the system to scale and decrease the heaviness of the first three functions. But try not to lose too much of the fast lookups that we have. But there will be a trade-off since we cannot have the fully connected network anymore. You can see global or view global kind of as a key value store. where the name is the key and the process ID is the value. And luckily for us, a lot of smart people have already thought about this issue. So it's a good opportunity to avoid reinventing the wheel. So what we want to base this on is a distributed hash table, which is really kind of a distributed key value store, where each node is responsible for a range of keys. And it's using consistent hashing to make sure that you don't have to update all the ranges in the system when new nodes join and so on. There is no centralized server or centralized synchronization here, so it's really decentralized, which we want to keep, so that's good. Any good distributed hash table is using or is guaranteeing big O log n lookup time, which makes them scale really well, and it also makes sure to replicate the name process ID pairs over multiple nodes, so it can handle node failures and so on. Yes. We have chosen to, there are many different distributed hash table algorithms, and we've chosen to base our new global version on Kademlia, which, just like most other ones, guarantees a big O log n lookup time and store time. It's a bit easier to maintain the Kademlia structure than many other distributed hash tables, and configuration information is spread around in the system during the lookups, which, and with configuration information, I basically mean information about which nodes we have and so on, so that each node's routing table can be updated only from the lookups. But there will also be some extra configuration messages sent around at least, but we can decrease that amount. Kademlia can be viewed as a binary search tree, where the nodes are the leaves in the tree. And each node has a node ID, which determines its position in the tree. So here we have an example of the nodes 0, 2, 4, 5, 6, 7, 10, 11, 12, 14, and 15. And this is, in this example, we use ID size of 4 bits, but usually we have a lot larger number or a lot larger size, maybe 160 bits or something like that, because otherwise it wouldn't work really. It would be too small. And this will also be the key space that you use. So we get the node ID by hashing the node name that I mentioned in the beginning. We know the node name to be unique, and we want a node ID to be able to put it in the, or give it a position in the binary tree. And we use a hash to do that, to give a good distribution of the node IDs. And this node ID is also used to determine which node is responsible for which keys. So each node ID will be responsible for the keys that hashes to, or key terms that hashes to a key which is the ones closest to the node ID. Each node has some subtrees or its own subtrees. So here is an example of the subtrees for node 15. And the subtrees are determined based on the common prefixes the nodes in each subtree have with the node the subtrees are for. So in this case, we have node 14, which is in the closest subtree, because it will have all the 3 first prefixes in common with 15. So it gets its own little subtree. And then the further away from node 15 you get, the greater the subtree you get. So in the last one, there will be no common prefixes, so that will be half of the subtree. And here is another example for node 7. And you can see that its closest neighbor also gets its own little subtree here, and the further away you get from node 7 is the bigger the subtree you get, or the less common prefixes. So we have subtrees, and from these subtrees we can each node guarantees that it knows at least one node in each of the subtrees, or its subtrees, and that builds up the routing table for each node. It can have up to k nodes per subtree, but always at least one. So the routing table doesn't grow infinitely, since we have this k limit, upper limit as well. And it might look something like this in our example. So node 15 knows at least one node in each of the subtrees, and so it knows node 14 since it has its own subtree, node 12 since it's the only one in the next one, and at least one in each of the other two subtrees as well. And here is the example from the node 7's perspective. So this will be the routing table for node 7. In Kademlia, we determine the distance based on XOR. So the distance between node A and node B will be the ID of node A XOR the ID of node B. So in this example, we have 7 or 0, 1, 1, 1, and node B has the ID 11 or 1, 0, 1, 1, and the distance between them will be 1, 1, 0, 0. And to determine which subtree you'll find the node in, or the key, or whatever you're trying to look up, you can mask out the most significant one from the distance. And in this case, we'll get 1, 0, 0, 0, which shows us that there are no common prefixes in this case. So node B would be in subtree 8 for node A, and node A would be in subtree 8 for node B as well. So we can see here that node 11 is in the subtree furthest away from 7, just as we calculated. Okay, so we have the routing table information. Let's do something more fun with this and look at the node lookups. And this is what is used to get closer to the key which you're trying to look up, or if there is no, or if you just do a node lookup, you'll locate the k nodes that are closest to the key. And this procedure is used for both storing lookups and also during the joins. So for when we call global register in this new version, we would locate the k nodes that are closest to the key, or the hash of the name in our case, and then we would store the name process ID pair on all those nodes. For where is, it should be name there too. Okay, never mind. For the where is function, we also use the same lookup functionality to get closer to the name, and then eventually we'll be able to return the process ID, and the same will happen during the send, but when we have the process ID, we'll send the message to it as well. So let's visualize this. So we have this name, which we're trying to look up, and this name happens to hash to 5, so 5 will be the key, and we'll try to look it up from node 15 here. And I'm showing a worst case example, just because it's good for the visualization. And also I don't use any replication in this example, which would usually be the case. But to make it simpler, we don't have that here. Since this name will be hashed to 5, we know that node 5 will be responsible for it, since we don't have any replication, and node 5 is the one closest to key 5. So, remember the routing tables for node 15. So node 15 does not know node 5, but the first thing it does is to XOR its own ID with the key it tries to look up, 5 in this case. And then it will mask out the most significant one to get to see which subtree it should look in. And this is because to avoid going through all the routing table each time you want to look up a value, but just to be to look through at most k nodes, which would be in the specific subtree. And then we see that there are 2 nodes in that subtree, node 7 and node 0. So we compare the distance to 5 for both of them using XOR again. And we can see that node 7 is the one closest to 5. So we ask, node 15 asks that node if it knows what the process ID for this name is or how to get closer to it. The node 7 does not know the process ID for 5 or this name, but it looks into its own routing tables to see how to get closer to it. And the one it knows to be closest is node 4, so it returns node 4 to node 15. And then node 15 can ask node 4 if it knows the process ID for this name or how to get closer to it. And the same happens again. Node 4 looks into its own routing table since it doesn't know the process ID. And it will return 5 since it's the closest neighbor, which it will know. And then finally we can ask node 5 if it knows the process ID, and we found the PID. So, great. This is called an iterative lookup, and it can be done in parallel. So if we go from the beginning, we would send out 2 messages at the same time to the 2 nodes we know to be closest, or even more messages depending on what parallelity level? How to say that? Yeah, you get what I mean anyway. What level of parallelity you want. And then the lookup would continue. So I'm not going through all those steps again. You can get the picture. You can also use a recursive lookup, which would look like this. So instead of returning how to get closer to the process ID or the key that you try to look up, each node will ask the next one itself, and then finally, when we found the process ID, it can be returned. I haven't made any measurements and investigated these 2, compared them to so much, but it seems like the recursive one is faster in most cases. But during the iterative one, you update the route. You're able to update the routing table in another way, because then you discover new nodes on the way. That can also be fixed in a recursive version by sending a few extra messages around. But yeah, since I haven't made measurements and so on, I'm not sure which way to go yet or which way we'll choose. So I thought it would be worth mentioning both of these. But we'll see which one we'll end up with. They both provide a big O log and lookup time anyway, in a worst case. Okay. So back to the global API. So I've shown how we can implement register name through this, and where is name and send. But one thing I haven't mentioned is that if a process dies, it should be re-registered and not returned from the global registry anymore. And since we don't want the extra connections, we cannot set up links or monitors on all the processes that each node is storing it in its own table. So we have to, unfortunately, add an extra message round trip during the lookup. And since we have we know which node the process is running on, we can easily just ask that node if the process is still alive or if it's dead. And if it's dead, we can return undefined. And also, if the node has crashed, we know that the process is also dead since it was running on, process is also dead since it was running on that node. And in that case, we can also return undefined. And the fact that we have to do that makes the unregistration and re-registration a lot simpler to implement. Since we already have that extra message round trip to the node where the process is running, we can decide that that node is the owner of the name process ID registration. So when doing an unregister, we can tell that node, okay, this process isn't registered under this name anymore. So during the where is, the last message round trip there, during the lookup, we can also ask if it's still registered or not. And the same thing goes for the re-registration, because it's basically an unregistration and a registration again. And this also makes caching a lot easier. Since we have this natural owner where the process is running, we don't have to, if we are able to save the name process ID somewhere else in the system, we can just go ask the node where the process is running if it's still registered and still alive, so we can avoid the extra message passing. And in that case, so we can optimize the lookup a bit further to try to mitigate what we're losing compared to the old version of global as well. We're also looking into how to improve the caching here, but we haven't decided on anything, so I can't go into any details about it yet. But we might try to improve it even further to avoid even that extra one message round trip. Great, so then we have implemented all the functions of global, and we've also tried to mitigate the lookup trade-off that we've gotten through caching. But we have the node joins left to look into. So I'm just going to show how it works when a node joins. And what happens then is, the first thing that happens is that you need one other node to connect to in the system. So, but that's the case for the old global version as well. You need one node to ping or something to connect to the network. Then you're looking up your own ID to get to know the closest neighbors or your closest neighbors, and then the node looks up one random ID in each of its subtrees. And so while doing this, it will both populate its own routing table and also spread around information about itself, so that other nodes can also find it during their lookups. Let's just look at this quickly. So node 8 is joining by pinging node 11. And it puts node 8 puts node 11 in its own routing table. And then it tries to look up itself, or key 8. So it asks node 11 how to get closer to 8. Node 11 knows that 10 is closer to 8, so it will return 10. And then node 11 will also try to add it to its own add node 8 to its own routing table if there is still space there. So we have found our closest neighbor. We'll also ask node 8 or node 10 for how to get closer to 8. And node 10 will return itself since it's the one it knows to be closest. And then it will add node 8 to its own routing table again, just as 11 did before. And after that, we will randomize one node ID in each of the subtrees from node 8. So in this example, I randomly chose node 10, 3, and 13. And we will perform a lookup on those nodes. And during those lookups, node 8 will populate its own routing table and make sure that it knows at least one node in each of the subtrees. I forgot to mention that it should also do a lookup on node 9, which is not very visible, but it's here. So it will notice that it doesn't have any closest neighbor as well. But if it was there, it would get to know it as well. Okay, so the node, and also I forgot to mention, the synchronization of name process ID registrations is a lot cheaper as well, since you don't have to synchronize all the name process IDs in the system, but only the ones that are closest to node 8 in our example, since that's what node 8 should be responsible for, with some additional replication. So now we have removed the need for a fully connected network, so we can start garbage collect connections. And so we'll try to bring down inactive connections while still making sure that you don't lose any messages while this is happening. So if you happen to send a message while we have set up a disconnection procedure, we'll either interrupt it and we'll be able to send the message over the same connection again, or if we have gotten past a certain step in the disconnect procedure, we'll have to disconnect, but then we'll set up a new connection anyway so that the message can still be sent. So you don't really have to care about this, that this is happening in the background. We'll make sure that the message is still sent so you don't lose any messages because of this. And actually we really need to fix this to be able, or to make sure that we don't get a fully connected network, because using Kademlia, we tend to talk to a lot of different nodes in the system. So if we don't start garbage collecting the connections, they would still stay up and we would end up with a fully connected network anyway after a while. So we'll need to add that before we can say we're done with this, improvement. So, do you think this would work better when the system grows? Well, I hope so, sure. Research supports that at least. We haven't gotten so far in the procedure yet, but I've made some initial measurements and it looks very promising. There is, as I mentioned before, and I'll mention it again, a trade-off with the lookups, but it's something that we have to do, unfortunately. There are a lot of more measurements, larger scales, and so on left to do. And a lot of optimizations and a lot of more details that needs to be implemented. So there are a lot of fun things left to do, which is lucky for me. Not so lucky for you if you want to use this, because you'll have to wait for it. I'm sorry about that. I am also going to mention some other things that we are discussing for the distribution, just in case one of you is interested in this. Jose mentioned in an email thread a few months ago that RPC is kind of a bottleneck. I've looked into that a bit and made some measurements. It looks like it's a lot better than when those measurements were done. And I've also made some further improvements, but we might still want to discuss the ideas that came up from that thread. But the small optimization I made is in the 19 release anyway, so it's improved a bit, at least. We also want to add a remote spawn monitor, which we don't have today, and when we have that, we can actually make some further improvements to the RPC module by using that spawn monitor. But we might have to wait for it, unfortunately, because we don't know when we'll get to the spawn monitor thing. We want to port the Erlang port mapper daemon to Erlang, and we have some contributions on that, which we are considering bringing into OTP. We want to make some improvements on the protocol that we provide for the Erlang distribution carrier. Right now, by default, we use TCP, but you can specify that you want to use SSL or TLS if you want to. But we might want to provide even more protocols to use, and we also want to make it possible to mix different protocols for different parts of the system, which is not possible right now. We want to fragment large messages, because right now, if you send a really large message over the distribution, it will delay other signals and messages that tries to get out on the same connection, because there is only one connection between two nodes. But by fragmenting the large messages, we can sneak in the other signals while the large message is still transmitting. So we want to add that. And finally, we also want to preserve subterm sharing to make sure that terms doesn't explode in size when copied because of a deep copy that is made there. Yeah. Feedback is always welcome. So you can, if you have any bugs or feature requests, please add them to our Jira, which is on bugs.erlang.org. Or you can, if you have any discussion points or questions, you can use our mailing list, which you can find under erlang.org/community. And there you can also find some other channels to contact us on, for example, our Slack and so on. And if you want to talk to me, you can talk to me during the conference. I'm really happy to discuss these things or other Erlang things and so on with you. Or if you want to contact me after the conference, you can use my email here, zandra@erlang.org. So thank you so much for listening.
Thank you so much for that talk.
Okay, yeah. Thank you so much for that talk, and thank you for tirelessly working on the foundation on which Elixir builds upon. So, big round of applause for that. Thank you. We've got time for a couple of quick questions before the break. Have you seen a hand in the air?
Hi, I'm curious what prompted you to start improving this scalability problem in distributed Erlang. I mean, distribution has been in the Erlang since the early days, as far as I'm aware. Why did you start to look into this now?
Well, it's been under discussion for a while, even before I joined the Erlang OTP team. But everyone else is so busy with other things, basically, and so I was fast to grab this part because I think it's really interesting with the distribution. And yeah, so when I joined, we got an extra person so we could be able to focus on this as well, basically.
It's more a comment than a question. It's kind of a response to the previous question. But I can think of a pretty good rationale, which is people, when they're building out large data centers for big data, key value stores, and you look in Java and try to sell that type of stuff in, then straight away they'd say something like Zandra will scale up to 1,000 nodes. That's quite a powerful motivator. When you look at Erlang, you say, well, what's going to top out? And you say it's 50 nodes. You can make big nodes. People don't like that so much. It's less resilient, perhaps. But it's definitely a really important change.
Yeah, thank you.
Do you see another hand over there? Go.
So it's great to hear this work is advancing. I assume it's a continuation of the work already done in Scotland a couple of years ago by Erlang Distribution.
Sorry, I didn't hear that.
Is this the continuation of the EC Erlang work done previously?
Which work? I'm guessing not then.
So the reason it was, when you mentioned the connections, inactive connections we dropped, is that effectively the mesh network between nodes and not the list of nodes that are known to Erlang, if that makes sense?
Oh, so you're asking about the nodes function, or?
Yeah.
Oh, okay, the list of nodes. Oh, sorry.
And the connection for sending messages to this other remote node, the list of active nodes is still maintained separately with that.
Okay, so we have talked about this issue. I wasn't able to fit that into the presentation, but the nodes function, there is an Erlang nodes function which returns a list of all the nodes that the node is connected to. And now it will not be connected to all the nodes in the system anymore, so it will change that property, because some people use this node to get nodes function to get all the nodes in the system for different reasons. We will provide a snapshot opportunity instead, but that will take a lot longer. So that way you will still be able to get all the nodes in the system, but it would be slower. And also we will provide the opportunity to actually still set up a fully connected network, but instead of being the default way, you might need to add a flag or something like that. And in that case you can still use the nodes function. Did that answer? Yeah, great. So.
Hi. I have one question, or actually just wondering how many nodes you test with your new performance test. Is it also like just 30 or? And second to that, I was wondering about how the replication works with the keys.
Oh, okay. So the first question, I think I tested with 350 nodes or something like that, but I used really quite large machines to test on, so I didn't use that much of a network delay and so on during the tests, but it was improved a lot compared to the old version of Global. But we need a lot larger tests before we can say that it will work for real, I think. The replication works so when you do a lookup for registration, you will return k nodes, and this k is a configuration variable. So you'll get the k nodes that are closest to the hash of the name, and then they will be those k nodes will be responsible for the name process ID register pair. So it will be replicated on all those nodes. So it's not replicated everywhere, but it should be sufficient enough if you don't have any very dramatic crashes in your system.
I have a small anecdote and a question. So the anecdote is that I was the meetings, right, we were talking about Erlang and scalability, and then everyone was saying, Erlang doesn't scale, and I was sitting there, I was like, what? You know, like, scalability is not a absolute property,
No.
right? Like, from a perspective, nothing scales because everything is going to reach a limit. So you need to quantify numbers. But numbers close when you say, hey, those things don't scale up to some throughput or to some amount of nodes, and it was exactly like 50 nodes what people found to be the limit, but that's the default limit. It's like you scale up to 50 nodes by default. Because as you showed, if you don't want to use the default distribution, you can just turn it off, and then you can run around and tell how the machines should talk to each other, and you can get beyond that. And that's how people, they're still getting to thousands of nodes connect to each other in Erlang, just because they disable the default distribution. A lot of this is to make the default distribution scale beyond that. So it was very interesting because, anyway, so the question is, so I am like node 15 and I do a where's lookup, and I found out that the PID is node 5. And after I do the lookup and I have the PID, I want to send like messages to it. From that moment, will 15 be temporarily connected to node 5 so I can send information directly? That's why these connections are important. Or when I want to send data, will it still go through the routing table?
You wouldn't send the data through the routing table because that would make it really hard to keep the message ordering guarantees that we have today. We're considering to add something like that in the future, but that's quite far in the future because we think this should be sufficient enough for a long time. So for the moment, you will send the messages directly to it. Yeah.
And on that note, I'm afraid it's time for a break. But Sandra will go around, so please do the wrapper during the break. Any other time during the conference to ask you more questions. A huge thank you once again.